Out of all the traditional diets that humans have consumed across the globe, we would think that the diet of the Arctic, where plant foods are scarce and the environment imposes a high-fat, low-carbohydrate intake, we would expect the diet of that region to produce ketosis. And yet the inhabitants of the Arctic have a genetic impairment in the ability to produce ketones. How can we explain this? And what does it say about whether ketosis is the natural state for human beings? Watch the lesson to find out more.
Ketogenic diet has neurological benefits. Why do we have to eat such an enormous amount of food?
Complex science, clear explanations. Class is starting now.
Hi, I'm Dr. Chris Masterjohn of chrismasterjohnphd.com, and you're watching Masterclass with Master John. We are now in our 37th in a series of lessons on the system of energy metabolism. And today we're talking about the curious case of CPT-I-A deficiency in the inhabitants of the Arctic. This is a stunning case of evolution where the environment of the Arctic selected for a genetic impairment in the ability to produce ketones. How can we explain this? Well, let's just start by talking about what CPT-I is and what its deficiency does. The slide on the screen was originally shown in Lesson 22, and it shows the role of CPT-I in transporting fatty acids into the mitochondrion. Fatty acids are activated to fatty acyl-CoAs in the cytosol. They come through the outer mitochondrial membrane through VDAC, and in the intermembrane space, they're exchanged with carnitine to make a fatty acyl carnitine by CPT-I. Fatty acyl carnitine goes through a translocase in the inner membrane, and then it's converted by CPT-II back to a fatty acyl-CoA. Carnitine gets freed and returns through the translocase to pick up the next fatty acid. We saw in that same lesson that CPT-I is the key regulated step in transporting fatty acids into the mitochondrion. In the fed state, malonyl-CoA accumulates in response to calories, anaplerosis, and carbohydrate, and it inhibits CPT-I, which inhibits the transport of fatty acids into the mitochondrion, thereby suppressing their being burned for energy in beta-oxidation. CPT-I has at least 3 isoforms that serve different physiological purposes. CPT-I-A is predominant in the liver and the kidney. It's responsible for ketogenesis and for producing the energy needed for gluconeogenesis and biosynthesis. These processes are most predominant in the liver, and the kidney sometimes plays some role in assisting the liver, and that's why we find CPT-I-A there. CPT-I-B is a different form of the same enzyme that's predominant in skeletal muscle and heart. There, CPT-I-B serves to allow fatty acids to be utilized for the needs of those tissues rather than to satisfy the needs of the rest of the body, as with CPT-I-A in the liver and kidney. CPT-I-C predominates in the brain. Its physiological purpose is poorly characterized. Presumably, it transports fatty acids into the mitochondrion in exactly the same way, but the importance of that for physiology has less research behind it. Of the 3 isoforms of CPT-I, only CPT-I-A has ever generated an inborn error of metabolism. That means that genetic defects that are very rare that impair the enzyme's ability have only been associated with the form of CPT-I involved in ketogenesis and the energy for gluconeogenesis. What happens in CPT-I-A deficiency is that there's inadequate acetyl-CoA for ketogenesis and inadequate energy for gluconeogenesis. Remember that even though the carbons for gluconeogenesis are coming from amino acids, lactate, and glycerol for the most part, the energy is produced in large part by beta-oxidation. If you can't make ketones and you can't make glucose, you wind up with a condition called hypoketotic hypoglycemia. Low ketones, low glucose. Usually, you have at least one or the other. But if you don't have ketones and you don't have glucose, you're not going to be able to feed the brain. The classical presentation of CPT-1A deficiency includes hypoglycemia in the newborn, or if it manifests first in children, lethargy and seizures in response to fasting, altered mental status, vomiting, diarrhea, fever, enlarged liver, possible coma and death, hypoketotic hypoglycemia, hyperammonemia, and a high ratio of free fatty acids to ketones. The hyperammonemia occurs because, as we'll talk about when we get to protein metabolism, we need acetyl-CoA to activate the urea cycle, which is how we take the excess nitrogen removed from amino acids and safely dispose of it as urea instead of allowing it to accumulate as toxic ammonia. And so the deficiency of acetyl-CoA leads to a loss of urea cycle function, which means that you can't safely get rid of the nitrogen and it accumulates as ammonia, and that's toxic to the central nervous system. The high ratio of free fatty acids to ketones is reflected by the fact that adipose can release the fatty acids into the blood, but those fatty acids will not make it into hepatic mitochondria to generate ketones. In its classical manifestation, CPT-1A deficiency is rare, and it's often fatal. The mutations are usually private. What that means by private mutations is we're talking about a specific mutation that only occurs in a single family. When you have a disorder that's characterized by private mutations, that means that there's almost as many individual mutations as there are patients. Because it's not like a genetic polymorphism where there's a few different types that spread through the population. It's so fatal that it rarely escapes the family where it originated. It leads to a complete loss of the enzyme activity, and so it's almost always fatal if not treated with frequent feeding because of the fasting intolerance and a high carbohydrate diet because the fatty acids can't be efficiently made into ketones. In the Arctic, there is what's called the Arctic variant of CPT-1A deficiency. This is a polymorphism known as P479L. It's a single mutation that not only is found to be on the family, it is actually the normal form of the CPT-1A gene throughout the entire Arctic. Unlike the classical manifestation where there's a complete loss of enzyme activity, there's about 20% residual enzyme activity. It's normal in Arctic populations with homozygosity, meaning getting the defective gene from both parents, rates of homozygosity as high as 88%. It's usually asymptomatic, but it causes low ketone production and high rates of hypoglycemia in response to fasting. The Inuit have 3 times the rate of infant mortality that you would expect, and that infant mortality correlates with CPT-1A deficiency among individuals and among the prevalence of this deficiency in the communities. So this does act as a metabolic disorder in the Inuit because it does cause fasting intolerance. It does cause low ketone production, and it does contribute to infant mortality. Yet, it's not so severe as to cause even symptoms, let alone death in the majority of people, providing that they aren't exposed to fasting very often. And it's become the normal form of the gene. This is stunning because it's the only example known of where a metabolic disorder has become a permanent fixture in a population. In the Greenland Inuit, 54% are homozygous, 38% are heterozygous, and only 8% of the population have the normal gene. In the Canadian Inuit, 88% are homozygous, 10% are heterozygous, and 2% have the normal gene. This is also the normal gene in Northeast Siberia, and it's not found outside the Arctic. So it's Arctic specific, and it's taken over the entire Arctic. The next reason that this is utterly stunning is because it became normal, the evidence says, not because of a founder effect, for example, which is where someone happened to move into the Arctic who had that gene and everyone there was born from them, and that's how it became normal. Rather, there was a selective sweep, which means that this mutation existed somewhere and the environment selected so strongly for that as an advantage that it just swept the entire population through positive selection to become normal. That is stunning because this is an impairment in fat metabolism. Why would the environment imposing a high-fat diet on the population positively select for an impairment in fat metabolism as beneficial? Take a look at this abstract. Arctic populations live in an environment characterized by extreme cold and the absence of plant foods for much of the year, and are likely to have undergone genetic adaptations to these environmental conditions in the time they've been living there. Genome-wide selection scans based on genotype data from native Siberians have previously highlighted a particular chromosome region containing particular genes as the strongest candidate for positive selection in that population. However, it was not possible to determine which of the genes might be driving the selection signal, so they performed an analysis here where they found the P479L mutation that we were just talking about in CPT-1A, a key regulator of mitochondrial long-chain fatty acid oxidation. Remarkably, the derived allele is associated with hypoketotic hypoglycemia and high infant mortality, yet occurs at high frequency in Canadian and Greenland Inuits and was also found at 68% frequency in our northeastern Siberian sample. Unfortunately, they don't say the heterozygosity and homozygosity of the Northeast Siberian sample. However, 68% frequency means that if you add up the two genes that each person has and you look at the percent of the total genes that are the CPT-1A deficiency, it's 68% of those. For comparison, in the Greenland Inuit that we just looked at in the previous slide, the frequency was 73%. So a 68% frequency means that it's almost as normal in northeastern Siberia as it is in the Greenland Inuit. They go on, we provide evidence of one of the strongest selective sweeps reported in humans. This sweep has driven this variant to high frequency in circumarctic populations within the last 6 to 23,000 years, despite associated deleterious consequences, possibly as a result of the selective advantage it originally provided to either a high-fat diet or a cold environment. They're reporting this as one of the strongest selective sweeps reported in humans. That means that this allele, which causes a metabolic disorder, was judged by evolution to be one of the most advantageous genes matched to that environment ever. So let's look at what this is probably doing biochemically. The Arctic variant is reduced to 20% of the activity of the normal version of CPT-1A. It's also been found to be less sensitive to malonyl-CoA inhibition, so that means that even though it's very low activity all the time, when the Inuit are in the fed state, there's not much inhibition. So in normal CPT-1A, you have high activity in the fasting state, low activity in the fed state. In the Arctic variant, you have this very low activity that remains largely constant between the fed state and the fasted state. What this should do is it should mean that fatty acids coming into the liver mostly do not enter the hepatic mitochondria because the CPT-1A is deficient. Because there's 20% residual activity, you get a slow drip of fatty acids into the liver's mitochondria, regardless of fasting or feeding. And what you do get is directed into beta-oxidation. Because the priority with beta-oxidation is to give the liver the energy that it needs and then make ketones, most of what does get into the hepatic mitochondria is going to provide the energy for gluconeogenesis. There will be a slow leak of whatever exceeds that amount needed to make ketones, but under most conditions, because very little is getting in the first place and your number one priority is gluconeogenesis, there's not going to be very much left over for ketogenesis under most contexts. Most of the fatty acids that would have entered hepatic mitochondria instead stay in the cytosol and they're directed into triglyceride synthesis. The triglycerides leave the liver and then they're taken up by heart and skeletal muscle. And the heart and skeletal muscle can burn the fatty acids directly using CPT-1B, which is not affected at all by the classical metabolic disorder or the Arctic variant. Now, you can see why, under ideal conditions, this could allow someone to go through life with very little symptoms. But you can also see why many things could go wrong. For example, let's say the fatty acids make triglycerides, but there's not enough choline to allow the triglycerides to exit the liver. Choline deficiency impairs triglyceride export and causes fatty liver. In addition, oxidative stress can also impair triglyceride export. And so if there's inadequate antioxidant protection, that also could trap the triglycerides in the liver. In that case, the person gets fatty liver disease and the energy does not make it back to heart and skeletal muscle. Those tissues will starve. If beta-oxidation is to supply energy for gluconeogenesis, that assumes that there's sufficient glucogenic substrates. Perhaps in fasting or in very low protein intake, that could be impaired. It also implies that there's sufficient oxidation of NADH produced by beta-oxidation in the electron transport chain. If there's nutrient deficiencies, other genetic issues, variations or defects, or toxins or anything that would impair the electron transport chain, you may need large amounts of NADH to shove it into the electron transport chain to get enough ATP. And if all you get is this slow leak of NADH, that might not be enough to make the ATP that you need for gluconeogenesis. So this is situated where, under ideal conditions, it can be compatible with health, but it could make a person more vulnerable to any of these other effects producing ill health. The normal effect of the Arctic variant should be to take someone from a balance between CPT-1A activity providing ketogenesis and CPT-1B providing fatty acid oxidation in muscle and heart to a massive imbalance favoring CPT-1B activity. What this means is that you largely lose the capacity for ketogenesis, but providing you feed the brain with glucose and you get the fatty acids to the skeletal muscle and heart, everything is A-okay. As we would predict, the Arctic variant has been shown to result in a striking lack of ketogenesis in response to fasting. In this study, they took 5 children who were homozygous for the Arctic variant, and they subjected them to a medically supervised 24-hour fast. On the left are free fatty acids, on the right are ketones. The shaded area represents the normal range for children of their age, and the symbols and lines represent the data for the individual children. You can see that the free fatty acid response to fasting was pretty much normal. However, this is the normal range for ketones in a 24-hour fast, and this is the data for the 5 children. Not only did they have a strikingly less than normal production of ketones, but the production of ketones during the 24-hour fast is close to 0. Out of these children, 2 developed symptomatic hypoglycemia, with blood glucose values reaching 50 milligrams per deciliter in one subject and 25 milligrams per deciliter in the other. So, although the Arctic variant is associated with health, it produces an inability to make ketones and a strong predisposition to develop dangerous hypoglycemia in response to fasting. How can we make sense of why an environment imposing a fat-based diet would provide incredibly powerful selective pressure for a genetic deficiency in the ability to turn fat into ketones, especially when it provides vulnerability to hypoglycemia in response to fasting and increases infant mortality by threefold? What I propose is as follows. The Arctic environment imposes perpetual ketosis on a population that has normal ability to produce ketones. If that person has everything else about their situation compatible with health, then the perpetual ketosis itself will be compatible with health. But if that person is forced into ketosis and they have a genetic susceptibility to ketoacidosis, or they have other precipitators associated with ketoacidosis that contribute to catabolic stress, like injury, illness, food deprivation, or high workloads, then with the right mix of stressors and vulnerabilities, that perpetual ketosis can be transformed into clinical ketoacidosis, which in the absence of medical treatment, which would certainly be the case in prehistory, would mean death. That means that there could be a fairly high risk of ketoacidosis in the population without that CPT-1A deficiency. And the CPT-1A deficiency would cause incredible protection against ketoacidosis. For a deficiency that has the downsides we've talked about, it must be the case that evolution judged the threat of ketoacidosis far greater than the threats posed by fasting intolerance and increased risk of hypoglycemia. It's important to realize that when we compare this hypothesis to our own experience with ketosis and the experience in the clinic or in the research studies, we have to realize that we have the ability to choose our diets. So if we don't tolerate veganism well, we are not likely to be vegan or stay vegan. If we don't tolerate ketosis well, we're not likely to stay in ketosis. In the Arctic environment, the person who didn't tolerate ketosis well, because they were vulnerable to ketoacidosis, for example, wouldn't be able to choose otherwise, and that's why the selective pressure would be so strong. To sum this up, environments that force very high-fat diets exert extremely strong selective pressure against ketogenesis. That means that evolution does not want us in a constant state of ketosis. And it makes the idea incredibly questionable that ketosis was the normal state of our ancestors. Certainly, occasional fasting-induced ketosis, yes. But ketosis from a permanent ketogenic diet, no. Additionally, there are many other arguments against that. For example, we know that there are starch-specific adaptations, like duplications in salivary amylase genes in human populations that make it clear that we consumed starches long ago in our prehistory. We also know that as you get closer to the equator, where we evolved, diets get higher and higher in plant foods. Now, this isn't an argument against the utility of ketogenic diets. What it is to set the context that the ketogenic diet is a diet that uses a biohack of our metabolism that is designed to support fasting to achieve specific medical, or health-related goals. To see that as a biohack, man, respect. But we can't look at this from the foundational perspective that this was the ancestral diet of humans. It wasn't, and evolution responded swiftly and strongly when the environment imposed that kind of diet as a permanent fixture. With that said, let's go on now in our future lessons in this unit to look at the ketogenic diet as an important tool that can be used to support health. All right, hope you found this useful. Signing off, this is Chris Masterjohn, chrismasterjohnphd.com. You've been watching Masterclass with Master John, and I will see you in the next lesson.